In this question, ray diagram of two lenses L1 and L2 is shown in the figure. We can see this beautiful ray diagram and we have to tell which of these option is correct. As you can see the option basically describe nature of each lens. Whether the lens is behaving as a converging lens or diverging lens, we have to tell that. So look at lens L1, look at lens L2, look at the ray diagram. Tell me, what is the nature of each lens? Converging or diverging? Now this is the question. How do we solve these types of questions? Very simple. Just look at the incident ray direction, just look at the refracted light direction, and then determine carefully whether the refraction caused the light rays to bend towards the principal axis or away from the principal axis. If the refraction caused the light rays to bend towards the principal axis, then the nature of the lens will be converging, otherwise diverging. Now let me show you an example. Let's say we have this lens. What do you think? Is it converging or diverging? Well, some people will say, well, we can see this shape, we recognize this shape. This shape always represents converging lenses. No, not necessary. It can also behave as diverging lens. Actually, it depends on whether the surrounding medium is optically denser than the medium of the lens or not. So, don't say that this shape will always represent converging lens. Okay? Okay. Now, if we don't go for the shape, how can we then tell whether the lens is behaving as a converging lens or diverging lens? So I will show you an example. Let's say we have these two incident light rays. So these are the two incident light rays. Now you can see they were initially diverging. Can you see that? Yes, they were diverging. Now after refraction, they will be bent. Now let's say after refraction, they are bent like this. Still they are diverging. Still these light rays are diverging, but we can see they are no longer that much diverging as they were diverging earlier before they encountered the lens. They are now less diverging. So what is the nature of the lens? The nature of the lens is converging. This lens is acting as a converging lens. Even if the final light rays after refraction are diverging in nature, still the lens caused them to bend towards the principal axis. Can you see that? Yes. That's why this lens is converging in nature. Okay? So this is the concept behind this question. Now let's look at lens L1. So is this lens converging or diverging? Well, it is converging. Why? Because we can see incident light rays were parallel to each other, and now after refraction they are converging. They are bent towards the principal axis. Okay, so lens L1 is converging in nature. What is happening for lens L2? For lens L2 we can see these are the incident light rays. Can we see that? Yes. Now these incident light rays on lens L2 are diverging. Okay. Now, after refraction, what has happened? They have become parallel to each other. Okay. So, after refraction, these light rays change their direction. And now, let's look at the change in direction. Change in direction can either be towards the principal axis or away from the principal axis. In this case, we can see the change in direction is towards the principal axis. Therefore, this lens L2 will behave as a converging lens. Okay. So both these lenses are converging in nature, and we can say option B, lens L1 and L2 both are converging. Option B is the right answer for this question. The refractive index of a converging lens is measured for violet, green and red colors produced by the same source of light and found to be mu V, mu G and mu R respectively. So sweet. For different colors, we are getting different refractive index. Wow. Now the correct relation between these refractive indices is, now we have to find the correct relation. Which refractive index has the highest value? Which refractive index has the lowest value? What is the correct order? That is the question. Nice. Question is understood. Okay, now let me tell you something important. refractive index depends on wavelength. Actually, when the light is traveling in vacuum, you can say that all the colors have the same speed. But as the light enters a medium, then for different colors, we have different speeds. For different colors, we have different refractive index. Okay. Now, one important point right over here. If lambda increases, if wavelength increases, then refractive index decreases. Just this much is sufficient to approach this question. If you remember this, you can just get the answer quickly. Now tell me the order of wavelength. Which wavelength is the highest one? You will say wavelength of red color is the highest one. Which wavelength is the lowest one? Wavelength of the violet color is the lowest one. And in between, we might have wavelength of green color. Good? Good. So this is the order of wavelength. Now, what would be the order of refractive index? Reverse. Okay. So, refractive index for the red color will be the lowest one. And then we have refractive index for the green color. And at last, we have refractive index for the violet color. This is the highest one. So, refractive index for the red color is the lowest one. And refractive index for the violet color is the highest one. This is the correct order. And we can see that option B is the right answer. Now we have given the answer. Now let me show you something as fun. I will show you an equation, Mr. Cauchy's equation. This equation relates refractive index and lambda wavelength. So this equation I will only write two terms, A plus B divided by lambda square. So this is the relation. You can see as lambda is increasing, refractive index is decreasing. That is cool. So even if you don't remember this relation, then it is fine. I just wanted to show the equation to you. Okay, don't worry about that. Now let me show you something else. Suppose we have a converging lens, and we are putting a green light, and we are putting a violet light, and we are putting a red light on this converging lens, and all these rays are parallel to principal axis. Now after refraction, what will happen? These light rays will be bent. Now you can see violet color suffers the most refraction, and here we have the focus for violet color, and then we have focus for green color, and then at last we have focus for red color. Okay, we can see that. So these converging nature for different color is different, and the only thing I want you to take away from this question is if lambda increases, refractive index decreases. Just remember that, and option B is the right answer for our question. A parallel narrow beam of light is incident on surface of a transparent hemisphere of radius capital R and refractive index 1.5 as shown. So we can see these parallel ray of light, and they are coming and striking a transparent hemisphere. And this hemisphere has the radius of curvature capital R. Okay. So this spherical surface has the radius of curvature capital R. This is important. Now we have to tell the position of the image formed by the refraction at the spherical surface only. So just after refraction at the spherical surface, the image is formed, suppose at this particular location. This is the image just after the first refraction. After this, we can see there will be further refraction, and this image will act as an object for the second refraction. But we don't have to go that far. We just have to tell the location of the image formed just after the first refraction only. Okay? So, how do we find the location of this image? This is the question. Well, just apply the formula for refraction at the spherical surface. Do we remember the formula? I will show you the formula. Here is the formula. mu2 divided by v minus mu1 divided by u is equals to mu2 minus mu1 divided by r. What is r? R is the radius of curvature of the spherical surface. For our case, we know this radius of curvature is capital R, don't we? We know this radius of curvature. Nice. Now, let's put everything with their appropriate signs. So, what we will do, we will try to find out the sign of R. How to do that? Well, first of all, let's see the surface. This is the spherical surface. So, we will measure everything from this spherical surface. So, we are talking about the first refraction. Let's measure everything from this spherical surface. Now, one direction will be positive, one direction will be negative. Which side represents the positive side? Which side represents the negative side? Can you tell that? You will say, well, that is simple. We know according to sign convention, the direction indicated by the incident light rays is taken to be positive. Exactly. So in this direction, incident light rays were traveling. So we will take this direction as positive direction. And the opposite direction will be negative direction. Nice, nice, nice. Now, R. Is R positive or negative? You can say R is definitely positive. R is definitely positive. Center of curvature is lying on the positive side. Right. So, we will just say, instead of R, we will write plus R. Now, what is mu2? Mu2 is given to be 1.5 and mu1. Mu1, let's take the outside medium to be vacuum or air. So we can say mu1 is actually 1. Now let me put the values. So I will just say mu2 divided by v. Instead of mu2, I will write 1.5. So 1.5 divided by v minus mu1, which is 1, divided by u. What is u? U is the object distance. Okay, so where is the object? Well, object is at infinity. Why? Because the rays are coming parallel to each other. Yes. So, object is at minus infinity. We take everything with sign. Now we will write mu2 minus mu1 divided by r. Mu2 minus mu1 will be 1.5 minus 1, which is 0.5. And we will divide it by plus r. Good. Everything is good. Now from this you can see V is coming out to be 3R. V is 3R. So this is the location of the first image formed by the first refraction itself. So this is the location. Now we can mark option B, 3R, as the right answer for this question. In a medium of refractive index 1.6, having convex surface, a point object is placed at a distance of 12 cm from the pole. The radius of curvature is 6 cm. Locate the image as seen from the air. And these are the options. Now I know you didn't understand the question at all. So let me explain the question with the diagram. Now let's go over here. Now we can imagine a convex surface. So this is our medium and this medium has convex surface. So let me draw the convex surface once more. This is our convex surface. How sweet. Now this surface must be having some center of curvature, right? So this is our center of curvature C. Good. Now this radius of curvature is given to be 6 cm. So we can imagine this distance to be 6 cm. Nice. Now, the question says the refractive index is 1.6. So, refractive index of this medium is 1.6 given in the question. All right, we are understanding everything. Now, the point object is placed at a distance of 12 cm from the pole. So, from this surface, let's place the object at a distance of 12 cm. So, this is our object at a distance of 12 cm. Nice. This is object O. Now the radius of curvature is 6 cm. Locate the image as seen from the air. So we have to find what is V. We have to find what is V. And it is said that image is seen from air. This means the outside medium is air. So what do you think is mu2? What is mu2? Mu2 is 1. Refractive index of air is 1. Now let's go on our mission of finding V. For doing that, I have to remove this question at all. So bye-bye question, boom. So let's see. What formula can we use? Mu2 by V minus mu1 by U is equals to mu2 minus mu1 by R. You remember this formula. Mu2 minus mu1 by R. Amazing. Now let's put some values and let's get the answer. So do we know mu2? Yes, we know. What is mu2? Mu2 is 1. Do we know V? No. We have to find V. What is mu1? Mu1 is 1.6 if we divide it by U. Now tell me, what is U? We have to put everything with signs. Remember that. So the direction in which incident light rays are traveling is positive. Incident light rays are emerging from the object. Okay? Okay. And the opposite direction is negative, obviously. So what is U? What is U? U is minus 12. Exactly. And then we have mu2 minus mu1. This is nothing but minus 0.6 divided by R. What is R? Come on, you can tell me what is R. Is it positive or negative? It is negative because the center of curvature is on negative side. Okay, so R is minus 6. Now from this we can find out what is V. V comes out to be minus 30 after some calculation. So image is at a distance of 30 centimeter from the surface. But image is lying on the negative side. Minus 30 means negative side. So where is the image? Image is right over here. This is our image. Oh, so this distance is 30 centimeter. 30 centimeter. Exactly. Now, let me draw a beautiful ray diagram. So, we have found out the answer. We are just drawing a ray diagram just for fun. Now, for drawing the ray diagram, I will draw the normal to the surface. This is the normal to the surface. Normal. Now, here comes the incident light ray. This is the incident light ray. Let me choose a different color. Green color will look good. So, let's choose this color. This is the incident light ray. Now, light ray is going from optically denser medium to optically rarer medium. So what will happen? Well, the angle of refraction will be more than the angle of incidence. So this light ray goes like this. Let me extend something from image, and we can see the direction of the refracted light ray. Good. So this is the direction of refracted light ray. And we can draw some other rays also. So this ray is striking at 90 degree. So we can see it will go straight on. Now these light rays are not converging at a point. They are appearing to diverge from a point. That's why our image is virtual image. So our eyes will be able to catch these rays and the image will be virtual image formed at a distance of 30 centimeter from the surface. So at a distance of 30 centimeter, we will get a virtual image. And let's see the options. Option B, virtual image at 30 centimeter. This is the right answer for this question. A denser medium, this means an optically denser medium of refractive index 1.5 has a concave surface of radius of curvature 12 centimeter. Now let me draw the curved surface. So this is our optically denser medium and this is the curved surface. And you can see it is concave. It is like a cave. Suppose there was a heavy rain outside and some early man wants to protect himself, so he can just go inside the cave and enjoy himself. Okay, so let's put the early man away and the rain go away, and let's start to focus on the center of curvature. Center of curvature is over here, and the radius of curvature, you can see its value is already given. It is 12 centimeter. So R is equals to 12 centimeter. Nice. And we can see that our first medium is optically denser medium. Its refractive index is 1.5. Good. This is the given information. An object is situated in the denser medium at a distance of 9 centimeter from the pole. So this is our pole, and at a distance of 9 centimeter from the pole we have our object. So this is our beautiful object, and the distance is 9 centimeter from the pole. Good. And we have to locate the image due to refraction in air. So outer medium is air. Mu2, we will call it mu2 as 1. Outer medium is air, and we have to locate the final image. Now, to locate the final image, we need two rays of light. The first ray of light emerging from the object goes like this, straight on, shoo, like this. And we can see angle of incidence and angle of refraction is equal to 0. And this ray goes straight on to pole and goes and enters the other medium. Nice. And let us draw another ray. Now this ray is very special, and we can see the angle of incidence is like this. So this is the angle between normal and the ray of light. Now you can see I have drawn a normal very carefully. It will pass through center of curvature. Okay. Now when the ray of light enters from optically denser medium to optically rarer medium, what happens? Well, it bends away from the normal. Exactly. So you can see after refraction, it will bend away from the normal. Let me draw it with white color. After refraction, it will bend away from the normal like this. So cool. Let me extend the refracted light, and we can see it is meeting over here. This is our image. This is the image. Now you can see after refraction, light rays are appearing to diverge from a point. That's why we will get a virtual image. This is not a real image. These light rays after refraction are not really meeting at a point. They are appearing to diverge from a point. That's why the image is virtual image. Okay. So we understand the image is virtual image. Now let's find the exact location. How to do that? Very simple. Let's make some space and let's use a simple formula. From that formula, we will get the straight answer. Now, the formula is like this. You remember the formula. It is mu2 divided by V minus mu1 divided by U is equals to mu2 minus mu1 divided by R. Very nice. This is the formula. Now let's put some values and get the answer. So mu2, what is the value? 1. What is V? We don't know. We have to find V. And we do know what is mu1. It is 1.5. Do we know what is U? What is U? Well, if you want to put the value of U, you have to do that with proper signs. Now let's see. If we move in the direction of light rays, we move in positive direction. If we move opposite to the light rays, we move in negative direction. Okay. So from pole, we have to see all the distances. So from pole, let us see the object. Is the object on positive side or on negative side? Come on, tell me. On which side we have the object? It is on the negative side. So what is U? U is minus 9. Oh, wow. And what is mu2 minus mu1? Well, mu2 is 1 and mu1 is 1.5. So mu2 minus mu1 is minus 0.5. And we divide it by R. Now let's see the direction. The direction is positive. The center of curvature is on positive side. So R is plus 12. Good. And now we have to simplify and calculate the answer. You can see that after some calculation, we will obtain the value of V. And V is coming out to be negative. So minus 4.8, this is the value of V. Now we can see in the figure also, the image is on negative side. Can you see? From the pole, the image is on negative side and it is at a distance of 4.8 centimeter away from the pole. Good. So we got the location of the image. And what is the type of image? Image is virtual image. We have talked about it. So virtual image at a distance of 4.8 centimeter from the pole. Let's see the options, and we can see option D. Virtual image at a distance of 4.8 centimeter from the pole. This is the right answer for this question.